Imagine you've got your morning cup of tea out, and you stir in your sugar, and so you suddenly wonder, can I actually track the motion of the sugar particles as they dissolve into the tea? It seems simple, right? It's just a spiral shape. But it's not that easy. Each molecule of sugar will behave differently and follow a wildly random path. To track the path of each of them is incredibly complex, and until recently, almost impossible. To trace the path of all the particles in a fluid is the objective of a set of equations called Navier-Stokes equations. Although they may look complicated, all of them are really just a fancy version of Newton's second law, F equals ma, which describes how objects change speed when a force is applied to them. Because fluids are a collection of interacting particles, we need to take into account the effects of particles, such as diffusion and convection. Then we need to consider its viscosity, which is a measure of how much the particles resist flowing over each other. The Navier-Stokes equations are the subject of one of the famous millennium problems. These are a set of open problems so important to modern mathematics that the prize for a solution is $1 million. The problem comes in two parts. First, you need to prove that there is a solution for all situations containing a fluid, which is called proving the existence of a solution. Next, the solution has to be both smooth and globally defined, meaning the solution is true for all situations, from all possible starting positions, and at an infinitely fine resolution. This seems pretty straightforward, so why hasn't the Navier-Stokes problem been solved yet? The answer lies in a phenomenon called turbulence. This can be seen in smoke. While the smoke may initially rise in a straight line, at a certain point it begins to curl and weave in a complex, unpredictable way. Likewise, when simulating a fluid, it would often reach a state when it behaves irregularly and unpredictably, similar to turbulence. In some situations, the Navier-Stokes equations tell us that some particle within the fluid is actually accelerating away at infinite speed. The acceleration becomes infinite because of something called a singularity. Picture this, you're stretching out a soap bubble until it suddenly snaps. The decrease in bubble size is so fast that we can call it infinite. This is what happens, just in equation form. We can see that since the nature of turbulence is unpredictable, providing a global solution for all the different states a fluid can be in is extremely difficult. So the Navier-Stokes equations can answer some pretty cool questions about everyday life, such as how an aeroplane flies, how blood flows through the body, and how long it will take a stirred cup of coffee to become still. Importantly, solving the Navier-Stokes problem may hold the key for us to finally understand turbulence. In the meantime, take a trip down to your local creek to observe turbulence in nature, and who knows, maybe you'll be the first person to truly understand turbulence.